Hello everyone, today we'll cover all what you need to know to do multiple comparisons with Affymetric analysis. So the first type of analysis that we will do is what to do when you have one sample type and you subject that sample to different types of treatments. So for example, we treat a cell line with 3 or 4 different drugs to see how this affects the transcript. We will start by usual loading our lemma library and the oligo and the tidyverse. And then we will load the phenotypic data in this txt file and we will create the expression matrix. So if we look at our phenotype data that we save in this data frame that we name targets, we have different files represented to this unique cell line that has been treated with, for example, 3 different drugs, A, B, and C. So now we want to understand how the expression of the mRNA is affected for the different treatment that we are using. So now what we want to do is to create a design matrix so that each treatment is considered as an independent group. And we look at the design that we have. The first 3 replicates treated with drug A, the subsequent 3 replicates with B, and the last 3 we have them with C. So now we want to do the multiple comparisons. We want to compare not only A and B, but we also want to compare B and C and A. And it's here in this make contrast that we indicate all the contrast that we want to do. So we want to test A versus B, so we do B minus A. Then we want to do B versus C, so we do C minus A. And then we want to do C versus A, and so we do A minus C. So we run all these. So we already fitted the model. Now we want to include the contrast, so we do this fitting to where we include the contrast that we want to make, and then we do the statistics here. And now we are going to call in all these data frame the different results, and here is where we specify the contrast that we want to look at. So in this case we want to start with B versus C, and if we go to the all stat, we have that for this probe ending in 038, we have log fold change of 1.73 when we compare B and C, and we have the adjusted p-value. So now if we want to compare A versus B, we do here, we change the contrast and we have the all stats now changing. So we have this probe now ending in 013 where we do see 1.67 log fold change between A and B, and also we have a significant value. So this is not very different to what we have done at the beginning. The main difference is that we include here all the comparisons that we need to make, so we don't have to repeat any of the functions throughout. Now things get a little bit more complicated when you have, for example, more than one cell type that you treat with multiple drugs. For example, we have cell type A that you treat with compound X and Y and Z, and then you have cell line B that you treat with a certain compound. So in this case, you not only want to make the comparison of how drug X and Y affects the gene expression of cell line A, you also want to see how the expression of cell line B is affected by treatment with X and Y. And more importantly here, you also want to see what are the genes that are affected in cell A when you treat with drugs X and Y that are not affected or are more affected in cell line B when you treat with the same drug. So this is asking essentially if there is any interaction between the treatment of the drugs and the cell type that you are using. Now we upload the phenotypic data that is in this pdata.txt. So we go ahead, we load that, and we create again the expression matrix. And if we look at these target files where we loaded the P data or the phenotypic data, it looks like this. So we have in condition, for example, the different cell lines. We have, for example, 2 cell lines, A and B, that we are treating with here 2 drugs, X and Y. And so here we have like A is treated with XY and B treated with XY. So this is a 2-factor experiment, and we want to see, okay, how X and Y affect the gene expression of cell A. We also want to see how X and Y affects the gene expression of B. And more importantly, we want to see what genes are affected when treating cell A with X and Y that are not affected when treated cell B with the same compound. So to do that, we go and create this following design that we are going to use. So here we created for each combination of cell line and treatment and drug one column. So we have cell A treated with X, cell A treated with Y, and the same for cell B. So this is our design. And here is where things change again. So when we make the contrast, we have the effect on treating cell type A. So here we specify that we want the difference between A treated with Y and A treated with X, and the same for cell B. And here is where we include this interaction term. We go ahead, we pass the fitted model this contrast that we are specifying, and here in the all stats table, we request here the different coefficients, and we can look at the, for example, let's start with what happens when we treat with A. So that's what we are going to look first. And if we go up and look at the all stats, we have this gene ending in 038, that you have again a forward log change of 1.77 and this adjusted p-value. Now we want to see, okay, is there any interaction between the expression of that gene in that cell type with the treatment of the different drugs? So here we enter the interaction coefficient, we run again, and we see that for this probe that there is actually not a significant difference in the treatment for cell A and cell B. So that's it. This is when you have a 2 factorial experiment. Last, we will see what happens when you have batch effects or when you have pair samples. So these samples have been treated in a special way, or they are linked because they have the same origin, or they were treated the same day. So we want to account for the experimental variability intrinsic to this lack of independence. So to control for these batch effects, we will treat the samples in the following way. Again, we loaded our libraries and we have our phenotypic data, and we will look at these targets data frame again. Here we have a similar situation as the previous one when we have the conditions. We have the treatment, so we have cell A treated with X, Y, and B the same. But then we know that, for example, AX1 and AY1 and BX1 and BY1 have been treated at the same time. So we want to account for the variability that is intrinsic to this group, and the same for the other groups here, 2 and 3. That's our phenotypic data. Let's look at this design. So when we do the design, we end up with something similar to what we had before, where we have, like, again, we create for each cell and treatment one column, and these are the 3 replicates of cell A treated with X, and the same for the other combinations. Right now, this is where things change at this point. This is before fitting the model. What we ask is for this duplicate correlation that we are going to keep in this core fit variable, where we give the expression set, the expression matrix, the design, and then we say, okay, which are the batch samples in this block variable, and these ones are those that are in the batch column. So again, if we look at our targets, this would be the batch that we'll be linking all the 1s, 2s, and 3s. So we do that, and then we pass that core fit variable to the fitting of the model. So here we have the express matrix, the design, and then here we have the block and the correlation that we want to pass to this fitting model. And once that is done, the rest is very similar to the previous case. We have the treatments here, and we have the interaction. And in all of this process, we will have accounted the batch effect for those samples that were treated or generated or were not dependent. And if we run this, we end up again with the all stats variable, where you have all the information, both for the interaction within each of the individual cells, and also for the interaction between cell type and treatment. So with that, we finish with mostly the analytical part. We also previously covered the quality control. In the next video, I want to share with you some tools that I use to present the data generated with microarrays, so don't forget to check the video. See you then.